These are the notes for 4.2, day 2. And before we begin, we're going to just do a review problem of a right rectangular approximation method, which is what that stands for. And I screenshot a multiple choice question off a previous AP exam. So first thing to do when you're doing these is read the question and take note of all the details. A tank contains 50 liters of oil at 4 hours. So if I were to draw a picture of that, I've got 50 liters of oil already sitting in this tank. Oil is being pumped into the tank at a rate R of T, so in liters per hour. They're pumping oil into the tank, and they've taken selected values of R and T at different time intervals. So what they're doing is saying at 4 hours in, it's being pumped in at a rate of 6.5 liters per hour. 7 hours in, it's being pumped in, but slower. 5 hours later, it's being pumped in and even slower. And at 3 hours later, at 15, it's being pumped in even slower. So what they're doing is the tank is being filled with oil, but at a slower and slower rate. But even so, the amount of oil in the tank will be increasing. It says use a right Riemann sum with 3 subintervals. What that means is you're going to make rectangles that hit on the right, and you're going to make 3 of them to approximate how much oil is in the tank. So really what I need to do is approximate how much oil got added in the tank in this time period, and then add 50 to it. Now I could go graph these dots and these points and make the rectangles, but the quick thing to do when you're doing these tabularly is to take in the fact that you're doing a right Riemann sum. So you're going to be sticking to the right. And when you look at the chart, if you were to graph all those dots, and I'm just going to make a cheesy one at 4, at 6.5, then went down and then down and then down some more. So let's suppose this was 4 and this was out 15, and I'm charting the R of T right here. And again, that's liters per hour, and this is just hours. When I'm using right rectangles, what that means is I'm going to go up and hit on the right, go over, go up and hit on the right, go over, up and hit on the right, go over. So I'm going to be using these right endpoints, and I'll never use the leftmost one. It basically, right rectangle means stick to the right. So what I need to do is figure out base times height of all the rectangles. Well, the base of every rectangle is the change in hours. So the first rectangle would have a base of 3, the second one would have a base length of 5, and the third one would have a base length of 3 as well. The height of every rectangle is where it hits the x-axis, but I'm going to stick to the right. So for this one, I'm going to use this right-hand one. For this, I'm going to use the right, and this, I'm going to do the right. And the area of a rectangle is base times height. So I do base of the first rectangle times height of the first rectangle plus base of the second times height, of the second, which is 5.9. I'm going to use parentheses instead of dots here, plus base of the next rectangle, which is 3, times its height. When you finish that up on your calculator, you'll get 64.9. But don't go circle A, because that's how much is being put into the tank. And again, when I'm doing this base times height, I'm doing an hour measurement times a liter per hour measurement, which does yield the liters that got put in the tank. But there are already 50 in there. So I have to make sure I take that and add it to 50. Now again, little review here. Had that said to do a left Riemann sum or left rectangles, I would have done it basically the same way. I still would have said base of 3, base of 5, base of 3, but then I would have stuck to the leftmost point, never using this one. So, and again, these are approximations for the area, or in this case, the liters. So if we're not making rectangles, we can get a really good approximation using trapezoids as well, because you'll see if I make trapezoids, I hug the curve a little better than I did with rectangles. The only thing is we need to figure out how to get the area of a trapezoid. So this is that same function from the last section of notes. It's the parabola x squared plus 1. I'm going to approximate the area under that curve by making 4 trapezoids. So a little review from geometry. I'm going to pull this trapezoid out and put it down here. For a trapezoid, you have 2 parallel sides, and those sides are always called the bases. It doesn't need to be sitting on its bases. They're the 2 parallel sides. And the perpendicular distance between those bases is the height of the trapezoid. So right here is actually the height of the trapezoid, and in the formulas we call that delta x, or the change in the x-axis. The formula for area of a trapezoid is 1/2 of its height times the sum of its bases. So if I were to find the area of each of those trapezoids for every one, I'd have to do 1/2 of the height times the sum of the bases, which I'm going to go do right here. So let's go estimate the area of this green shaded region under the parabola y equals x squared plus 1. In order to estimate the area of the entire region, I'm going to have to do the first trapezoid, plus the second trapezoid, plus the third trapezoid, plus the fourth trapezoid. And I'm going to do them all separately, and then I'm going to give you the formal rule that's in your textbook, but I'm going to advise you not to use it. I would actually do them all the way I'm going to approach this one. So first thing I'm going to do is I'm going to go look at trapezoid number 1. Every one of these has an area of 1/2 of the trapezoid's height times the sum of the trapezoid's 2 bases. Each one of these has the same height because I have a change in the x-axis here on all of them of 1/2. So I've got a height of 1/2, a height of 1/2, height of 1/2, height of 1/2. So when I start using my formula 1/2 of the height for the area of trapezoid 1, I'd have 1/2 of 1/2 times the sum of the 2 bases. So I need this base, which is 1, plus this base. And this base is the height on the curve at x equals 1/2. So if I put 1/2 in here and square it and add 1 to it, I'll have 1 1/4 or 5/4. So this is the point, 0.5 comma 5/4, which means this base has a height of 5/4. There's trapezoid number 1. Trapezoid number 2 has the exact same height, so I would do 1/2 of its height times the sum of its bases. Well, its bases, its left one is this, which I already calculated, 5/4, plus its right-hand base is what I get when I put 1 into the function, because this would be the point 1 comma 1 squared plus 1. So that base is too high. Plus, trapezoid number 3, I'm running out of space here, is 1/2 of its height times the sum of its bases. Well, its left base, I already calculated. It's this 2. Its right base is what I get when I put 1 1/2 into the function. It would be 1 1/2 comma, and it ends up being 13/4 if you plug a 3/2 in there. And finally, trapezoid number 4 is 1/2 of its height times the sum of its bases. Well, it shared this one with A3, so it's 13/4, plus this one, which would be what I get when I put a 2 into the function. So 2 squared plus 1 is 5. Now, that's kind of a long, strung out formula there. Let's clean it up a little. Let's notice what's in all of these. 1/2 times 1/2, or 1/4, is in every part of the sum, so I'm going to factor it out. Then I would have 1 plus 5/4, plus 5/4 plus 2, plus 2 plus 3/4, plus 13/4, 13/4 plus 5. You'll notice that I have 2 of all of them except the bookends. So it looks like this. It'd be 1 plus 2 of the 5/4, plus 2 of the 2's, plus 2 of the 13/4, plus just 1/5. Now let's go back to the picture, and you'd go do that on your calculator and crank it on out. Let's go take a look at how that makes sense up on this picture, which is getting a mess, so I'm going to erase some of this stuff. Notice graphically, this is only the base of one of the triangles. Sorry, I had to answer the phone. So what I was saying was, graphically, this kind of makes sense what you've got going here, because this base only gets used once. It's the left-hand side of trapezoid number 1, whereas this base is the right-hand side of number 1 and the left-hand side of number 2, so it will get used twice. Likewise, this one right here is the right-hand side of trapezoid number 2 and the left-hand base of trapezoid number 3, etc. This one over here only is the right-hand side or right-hand base of trapezoid 4. So they all get used twice except the bookends. So what that looks like formulaically, which I would suggest you don't use the formula, is you do 1/2 of the base. The base is the change in the x-axis. In the above example, it was 1/2. And then in parentheses, you do the height of the very first trapezoid, which was the f value at 0. So we say f of x sub 0. Then you do 2 of the next base and 2 of the next base. And you do that all the way to the end where you only do 1 of the very last one. And this is for n trapezoids. I would say, though, do not memorize this because you'll never remember it. Just think it through. It's all about the area of a trapezoid, which again is the half of the height times the sum of the bases. So we're going to do one algebraically. And then the rest we're going to do more like you'd see them on the AP exam with tables. So take out your graphing calculator and enter this under the y equals. We're only going to be looking at a portion of the graph. So go to your window on your calculator, set your x min to 2, your x max to 5, and go by ones. Set your y min to, I'd say 0. And then if I put a 5 in here, I'm going to get 2 times 5 squared, about 50 minus a few. I would go from 0 to 50 by 5s. And go ahead and take a look at the graph of that. You shouldn't be surprised that it's a parabola that opens up because it's a quadratic equation with a positive 2 in front of it. So let's go 1, 2, 3, 4, 5. And the parabola is going to open up. And let's just go like that. And I'm looking at this portion of it. And I want to find the area underneath it, approximating it by doing 6 trapezoids. Well, in order to do 6 trapezoids, I'm going to have to cut each of these distances in half and have my change in x be a half. So I'm going to do 1 trapezoid, 2 trapezoids, 3 trapezoids, 4 of them, 5 of them, and then last 6 of them. They each have a change in the x-axis or a height of a half. Now the easiest way to do these algebraic ones where they actually tell you what the function is to now go make your table do the work. So go on your graphing calculator, make sure your table set, make sure you have the independent variable set to ask. So hit second and get table set and make sure you're on ask. And then when you go to your table, you can just type these in and it'll give you the heights along there. So what this table is telling you is that this is 5 high, this is 9 high, this is 14, this one here is 24, nope, 20, this one's 27 high, 35 high, and 44 high. So when I write my equation to estimate the area, this is what I have. All the change in x's are a half. All the heights of all the trapezoids are a half. So I would do 1/2 of the height times the sum of the bases. Well, the first one would have been 5 plus 9 for this one plus this one. The next one would have been 9 plus 14 for this one plus this one. The next one would have been 14 plus 20. And you'll notice what happens is you're going to get 2 of all of them, except the y values at the bookends. So you can put beefy brackets and say, well, I'll just have the 5 once, but then I'll have 2 of the 9s, because this one gets used twice, and I'm going to have 2 of the 14s, 2 of the 20s, etc. Let's do 2 of the 35s, but then I'll just have 1 44. And then you can go enter that on your calculator, and that'll give you a number, and that number is an approximation for the area under the curve. But the trapezoids do a pretty good job of estimating. So now let's do it more how you would see it on the AP exam, which is with the tables. So what we've got is a car coming to a stop 5 seconds after the driver slams on the brakes. As he slams on the brakes, his velocity, so you can see he's slowing down because he hit the brakes. And we're estimating the total distance. This would be like the length of a skid mark created when he does that, maybe like in a crime scene analysis. So what you would have to do, so what I'm going to do here is, let's do a right rectangular approximation, also called a right Riemann sum, and let's do a trapezoidal approximation. Notice that when I'm thinking of the area model and doing my basis times my height, feet per second, times seconds does yield feet. So when I multiply, I will have an ending answer that ends in feet, which will give me the distance. So if I were making right rectangles, rectangles are all about base times height. The base is given by the change in the x-axis, which in this case would be the time axis. And again, I don't want to have to go plot all those points. You certainly could, but you would notice that on your time axis, they're all going to be 1 apart. So all my bases are 1. My heights, I'm supposed to stick to the right, which means I will use the right endpoint of the rectangles, not the lefts. So this one will never get used. So it's really 1 times 60 plus 1 times 40 plus 1 times 25, or equivalently 1 times 60 plus 40 plus dot, 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 plus 0 at the end. And that's all about rectangles, which is base times height. Because that was a decreasing function, like even if I go draw one, when you do right rectangles on a decreasing function, you get an underestimate. So you'll notice that this is going to yield, whatever the answer to this is, which I don't have a calculator on me, will be under the actual amount. If I'm estimating with trapezoids, what that means is I'm going to start here and I'm going to start making these trapezoids as I go along. And my formula is I take 1/2 of the height. Well, these now represent the heights of the trapezoids. So I do 1/2 of 1 times the sum of the bases. I would only use the 88 once because it's only going to be the leftmost of this one. I'd only use the 0 once, but all the others would get used twice. So I do 88 plus 2 times 60 plus 2 times 40 plus 2 times 25 plus dot, dot, dot. I won't dot, dot, dot it, plus 2 times 10, and then only 1 0 in there, or equivalently nothing in there at the end. You would add that all up, and that will give you a trapezoidal approximation. So I'm going to skip to the next one here, and this will be the, this will be the last one that I do. This one says readings from a car speedometer at 10-minute intervals. That's important that it says minute, so highlight that. During a full hour are given in the table. The speed is given in miles per hour. So what you should do is this is miles per hour and this is minutes. And when you do miles per hour times minutes, nothing cancels. And you want to figure out at the end the total distance traveled. So you want miles. What that means is you need to convert your unit of time to hours. So instead of this being a 10-minute span, we're going to say it's 1/6 of an hour. So again, you need to have matching units of time. So let's go. We're actually doing this at 10-minute intervals, but that's 1/6 of an hour. Now, if I do miles per hour times hours, I will yield miles. So we're going to use an RRAM. Let's go take a look at what that would look like. So for a right rectangular approximation method, I'm going to do my bases times my height. All my bases will be my change in the t-axis, which is 1/6, and it's consistent, so I can factor it out. It's really 1/6 times all the right sides. And it'd be 1/6 times 40 plus 1/6 times 55 plus 1/6 times 10, but I'm going to factor that 1/6 out and just do 40 plus 55 plus ... plus 45. Had it said LRAM, I would have stuck to the left and never used the 45 over here. And again, you'd go to your calculator and the answer would yield an estimate for the miles traveled. Let's also do an MRAM. This is midpoint rectangular approximation. So again, it'll all be about the bases times the heights. I'm going to take this off right now. For the midpoint, you don't know what's happening right in here at 5 minutes. So to accommodate that, what you do for the midpoint is you just make half as many rectangles. So instead of making 6 of them, I'm going to make one rectangle from here to here, one from here to here, one from here to here. What that does for my rectangles is it doubles the length of all their bases. So this would be a 20-minute interval, or a third of an hour, a third of an hour, and a third of an hour. So I'd have 3 rectangles, and I now know that in the middle of each of those intervals, I know the value. See, with the table, I can't figure out what happened at, like, say, 25. I have no idea, so I have to expand my interval length. So when I do base times height of my 3 rectangles, it'd be 1/3 times 40 plus 1/3 times 10 plus 1/3 times 32, or equivalently, 1/3 times the middle value, the middle value, and the middle value. And that'll give me the midpoint approximation. And again, when I'm multiplying my hours times my miles per hour, it will yield an answer in miles. Let's also, though, put a trapezoidal one on here just to keep that one going. So I'm going to make 6 trapezoids. And each trapezoid has 1/2 of the height times the sum of the bases. So I go up, and again, I'm going to do 6 of them. So I'm going to use the 1/6 is the height of all my trapezoids. So I'd have 1/2 times 1/6 times base 1 plus base 2, and then this base plus this one, then this one plus this one. So they're all going to get doubled except the bookends. So I'd have 26 plus twice 40 plus twice 55 plus twice 10 plus twice 60 plus twice 32 plus 45. All right, and these are all approximations for the area under the rectangle, all giving us miles traveled. So one thing to note, just, whoopsie, I'm going to go up. Actually, I think what I'll do is just make a fake one. On the worksheet, what you really have to watch for, most of them do have a consistent change on the x-axis, but if they don't, like if this goes 2, 5, 7, 10, 15, and then maybe this is, I'm just going to go 4, 5, 6, 7, 8, just to keep it easy. If you are doing a, let's say, an RRAM on one like this, so basically, base of rectangle 1, base of rectangle 2, base of rectangle 3, base of rectangle 4, you have to do them all separately. Nothing can factor out. And for an RRAM, you're going to stick to the right. So you would use these 4. So you'd say base times height plus base times height plus base times height plus base times height, giving you an answer. For the trapezoidal, it is really kind of a pain when these are not consistent along the t or the x-axis, because you have to do each trapezoid separately. What it'll look like is this. Trapezoid number 1 will be 1/2 of its height times the sum of its bases. Trapezoid number 2 will be 1/2 of its height, which would be 1/2 of 2, times the sum of its bases, which would be 5 plus 6. Trapezoid number 3 would be 1/2 of its height times the sum of its bases, which would be 6. And again, the heights, or the f of x's, are giving you those base lengths for your trapezoid, and the change in time is giving you your height of every trapezoid. So it'd be 1/2 of 3 times 6 plus 7, plus 1/2 of 5 times 7 plus 8. You really can't clean it up. Yes, these are all getting doubled in here still, all but the bookends, but the multiplier out front is different because the heights are not uniform. And that's the end. Have a good one.